Okay. So thank you for the opportunity to speak here. So yeah, I'd like to talk about some combinatorial description of embedded contact homology for specifically for T3 with certain contact forms. So to start, embedded contact homology or ECH is an invariant of a contact three-manifold. And it's isomorphic to Heegaard Floer homology and Seiberg-Witten Floer homology. So one might ask, if it's isomorphic to Heegaard Floer homology and there's already a combinatorial description of Heegaard Floer homology, why would I want to compute ECH directly? So one of the answers could be that ECH in itself is less, not as well understood as the other two homology theories. So to give an example of that, ECH, the definition of ECH chain complex depends not only on the contact structure, but also the contact form and the almost complex structure on the symplectization. And we don't know how to show that the homology is independent of those choices without referring to the isomorphism theory, isomorphism with the other theories. And also there is a ECH cobordism map, which intuitively you would expect to be able to define by counting rigid holomorphic curves in a symplectic cobordism between two contact manifolds. But there's a problem with multiply covered holomorphic curves, and right now it's defined using the isomorphism and using the cobordism map in Seiberg-Witten Floer homology. So these are difficult problems that we would like to understand a little bit better. And to start, I'd like to study some combinatorial descriptions of simple contact manifolds where I can give an explicit presentation of the chain complex itself. And another more practical motivation for studying this is that ECH depends on the contact form. Therefore, it encodes some contact symplectic and contact geometric data, quantitative information. And this information is lost under isomorphism because these two other theories do not depend on contact form. So for example, there's ECH capacities, which has been used effectively just recently to study like symplectic embedding problems. Those you could not apply just by knowing the homology by computing it through Heegaard Floer homology. So these are the reasons why you would want to study the chain complex by itself. Okay, so let's start with a quick definition of ECH. So let's start with Y be a three-manifold and lambda contact form on Y. So you have the contact structure C and ray vector field defined as the kernel of d lambda normalized by condition. And let's also assume that that this is non-degenerate contact form. So we need that in order to define ECH. And let's let J to be a generic admissible almost complex structure on the symplectization r plus y. Let S be the coordinates for the r factor here. So that means J is R invariant, and it sends the S direction to the rate vector field, and it sends the content structure to itself. So that's the setting. And we define the ECH chain complex. Maybe I should have used the board already. The ECH chain complex is then generated. So we'll use z/2 coefficients for simplicity by admissible orbit sets. So the orbit sets are finite set of pairs alpha I, comma mi, where alpha I are distinct embedded wave orbits. And mi are the multiplicities and admissibility condition requires that mi is in fact just 1 whenever alpha I is hyperbolic. So each wave orbit in a three-manifold is either elliptic or hyperbolic depending on the eigenvalues of the return map over the wave orbit. And for some mysterious reason, for ECH, you want the multiplicity to be 1 whenever it's in hyperbolic orbit. And let's say beta j, and j be another admissible orbit set. Then the differential coefficient between alpha and beta is defined by counting the moduli space. This moduli space of holomorphic curves from alpha to beta. So what I mean by from alpha to beta is that the positive infinity ends of the holomorphic curve at any of these alpha I must have exact multiplicity mi for each alpha I, and negative infinity ends must have multiplicity nj at each beta j. So M1 alpha beta is a moduli space of j holomorphic curves. Let's call it C. So from alpha to beta. And this subscript 1 refers to the fact that we want ECH index of C to be 1. So this is the ECH index. And it's slightly different from the usual Fredholm index. And for simple curves, it bounds the Fredholm index from above. So in this particular case, this condition implies that, in particular, C is embedded, hence the name embedded contact homology. And Fredholm index is also 1. Therefore, modulo R, you can count them. Oh, there's also compactness theorem for this setting so that this count is well defined. So that's the quick overview of the definition of ECH. Okay, now I'd like to talk about T3 with T2 invariant contact forms. But before I deal with the general case, I'd like to go over the original paper by Hutchings-Sullivan. So this is 2005, 2006. So it's fairly early days of the development of ECH, where they gave a combinatorial description of the ECH chain complex for T3. We'll use R mod Z3 with coordinates x, let's say x T1 and T2, with a particular contact form given by and for the sake of generalizing later, let's write this as minus g dt1 plus f dt2, where f and g are real valued functions, in this case, z periodic. Okay. And also, for simplicity, let us restrict our attention to, let's only consider holomorphic curves inside, let's say, minus epsilon to 1 minus epsilon times T2, T1, T2. So it turns out that all the ECH index 1 holomorphic curves in the symplectization of this T3, in fact, is contained in R cross some interval of length at most 1 times T2. So that's some index calculation that guarantees that. There's some subtlety that I'm glossing over, but just considering this case will be enough to illustrate mostly what's going on. So let's just do that. And so if you were to graph f comma g, so you start from somewhere here, and then it's just a circle. So this particular contact form corresponds to the graph f comma g that looks like this. And we can easily compute that the ray vector field is proportional. So in general, this is in general for any f and g. It's proportional to f prime dt1 plus g prime dt2. So whatever tangential vector that you find on the graph of f of g is telling you the direction of the ray vector field. So in particular, for this case, ray vector field is rotating counterclockwise as x progresses. Right. So what this means is that there is an S1 family of closed embedded wave orbits at each x. So remember, x is the coordinate for this vector here. At each x where f prime x over g prime x is rational. And the definition of ECH chain complex requires non-degenerate, so we're going to perturb this Morse spot setting by using a Morse function on S1 with 2 critical points. So instead of this S1 family, you're going to get 2 wave orbits. So one of them I'm going to write E check. And so this is an elliptic wave orbit corresponding to max of the Morse function on S1. And then you get another one, which is a positive hyperbolic wave orbit corresponding to the min of this auxiliary Morse function. Okay. And to write out the orbit sets, let's also introduce notation that. So this happens for each x where f prime over g prime is p over q. So let's write EPQ for elliptic wave orbit in homology class PQ in the first homology of this fiber torus, 2 torus. And HPQ for the positive hyperbolic orbit in homology class P comma Q. And also write an orbit set in ordered product notation. So by that I mean I'm going to write out each orbit that's appearing in your orbit set with multiplicity in the order of their x coordinate. So for example, in this case, you have multiplicity 2 at orbit 1, elliptic orbit 1, 0, and 1, 2, and 0, 1. So this is the orbit set written in the original notation. I'm just going to write this as 1, 2 squared, 1, 2, H0, 1, as a product of these orbits. So in this case, this orbit 1, 0 is here, and then hyperbolic 1 happens somewhere over here, and then another hyperbolic somewhere over here. So I've written these in the order of them appearing as x increases. So this notation is going to be unique up to permuting some of the elliptic and hyperbolic factors that's occurring at the same x coordinate. Yeah.
When you say perturb using a Morse function, so are you saying that you can perturb so that to get a contact form so that the only wave orbits are, because they're all very close to each other?
Oh yeah. So okay. So I was just ignoring that part. So we can compute ECH by what's called filtered ECH complex. So for that, we're just going to restrict our attention to orbit sets with action less than some L. And then the full ECH will be computed by taking direct limits. So when you do the filter version, then there are only finite many, and you can do the perturbation. So yeah, thank you. Right. So the idea there was to represent this as a polygonal path. So how many do I need? So by that I mean I'm going to write the vector 1, 0, and then I'm going to write another one because there's 2 of them, and then 1, 2, and then 0, 1, and then I also have to remind myself what kind of ray orbits they are. Right? So that's pretty straightforward. And then let's pick another orbit set. So this one is 1, 0. Oops. And then 1, 1 twice. And then 0, 1. And then this is elliptic, 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 and hyperbolic. Right? And the theorem is that Hutchings-Sullivan. So again, for simplicity, we're just going to assume that we're considering this with some nice perturbation of lambda, so given by this, and some nice almost complex vector J. So we'll just assume that. Then if alpha and beta are admissible orbit sets, then the differential coefficient is non-zero if and only if alpha can be written as gamma 1 times some other orbit set alpha prime gamma 2, and beta is gamma 1 some other orbit set beta prime gamma 2, written in ordered product notation. So they have to, all the orbits here should occur before any of the orbits here, and so on. So alpha and beta have common initial orbits and common final orbits, and something differing in the middle. OK, I forgot to give some notation for this. So we're going to use a notation P alpha and P beta for these polygonal paths. So alpha and beta are just admissible orbits.
Alpha prime and beta prime.
Oh, I'm not done. Yeah. So if and only if you can write alpha and beta in this way, and alpha prime. Sorry. The polygonal path corresponding to beta prime. Sorry. Let's say this first. The path corresponding to alpha prime has exactly 2 edges. So by edges, I mean the primitive vectors appearing in your polygonal path. And P beta prime is obtained from P alpha prime by rounding the corner. Between those two edges. And I'm still not done with the statement. Maybe I should write it here. And all but exactly one edges are labeled. So by labeling, I'm referring to the E checks and H checks. H check if it's an alpha edge, sorry, alpha prime edge, and E check if it's beta prime edge. So I have to explain what I mean by rounding the corner here. So I refer you back to this example of a pair of polygonal paths. So this P alpha and P beta share those two edges, and then those two edges, and something different in the middle. And by rounding it, I mean this middle piece has two edges, and I just take the convex path by imagining it's an elastic band, and you remove this peg, and then it'll be whatever convex path you get by doing so. Yep?
So there's a unique way to round every edge?
Right. So in terms of just the path, underlying path, there's a unique way, but there might be multiple ways of labeling them. So in fact, in this case, oh, I'm sorry.
You can enable the other edges in alpha and beta with whatever you want, as long as it's consistent.
Yes. Sorry. I forgot to say here. Oh, no, I did say it. Okay, sorry. So all but exactly one edges are labeled this way. So I rephrased the thing, so I was a little confused. So if you look at this example, these three are labeled by whatever condition that's staying there. So this is an alpha edge, so it's labeled hyperbolic H check. And these are beta edges, so it's labeled E check and E check, except this one, which should have been H check, but it's labeled E check, right? So this this region between the two paths satisfy the condition that's written there. Is that clear?
Doesn't it say? Oh, okay. All but exactly one.
Right.
Of the alpha prime and beta prime.
Right. So initially, so the way I think of it is initially always label them hyperbolic for the two alpha edges, and all the beta edges I label them E check, and then I pick one and replace it. So in this case, I replace that one. So in fact, yeah, I could have done that, but I wanted to illustrate, for example, the differential of E10 check squared times H 1, 2 check H01 check. So if I wanted to compute the differential of this guy, then I will look at this corner and round that corner, which gives me E check, E check, E check, H check. And I didn't have a choice of relabeling any of this because this already was the special one that got to be exception to the rule. So these two have to be, I had no choice but to labeling them E check. So this would be E10, exactly this one. But there's another corner here, right? So I have to consider all ways of rounding corners. So there will be another term in the differential, which is obtained by rounding this corner, which looks like, maybe I'll use green. So is it? So it looks like 1, 0, 1, 0, and 1, 3 obtained by rounding this corner, right? Is that clear? So there's another term, which is E10 check squared H13 check. Oh, sorry. I forgot to talk about the labeling. So for those ones, this one had to be E check and E check. And here, you have A check and H check, which conform to the rule. So this one better be the exception to the rule. So this one better be H check as well, right? So there's the quick review of Hutchings-Sullivan paper. And now what I want to do is extend this for any general contact T2 invariant contact form.
Sorry, is the
Yeah.
statement that del alpha paired with beta is 1, like there? Or
Yeah, I'm using Z2 coefficients, so it's either 0 or non-zero. Yeah. So if you were to consider the orientations, you would, I think you would still get 1. But for simplicity, we're just using Z2. Okay. Okay, so to illustrate the point that was brought up about multiple ways of labeling, let me do another quick example, hopefully. I won't be running too late. So this time, let me just write it in pictorial. So in this case, my alpha is, oh, I never needed all. So if this is my alpha, then what kind of terms are in the differential of this? So there's only one corner here, so I'm going to round this corner. So what happens is that you get this path right here, right? And that's the only way. So you have to get these. But since these are both H's, one of these two gets to be elliptic, and one of them gets to be hyperbolic. So there are two choices. So in fact, there are two terms in the differential. And right, is this clear? So you're summing over all possible cases where this condition is met. No. It's any convex path above that, strictly above that.
But there's also a straight line in this case, right?
No, it doesn't have to be a straight line.
There is also a straight line that's convex that's a,
This one?
Don't worry about that. Yeah.
Like this one?
yeah.
So if you rounded corners on this beta path, would you get a straight line?
Right. So what I mean is that it has to be the very next convex path above that one. So if you imagine this to be an elastic band, and if you remove this peg, then you will get that convex path. You won't be getting this one until you remove this peg also, right? So this has to do with the ECH index. So every time you remove a peg, you're sort of increasing the ECH index. So in order to just consider ECH index 1, you're only allowed to remove one peg. So, okay?
But it is possible, though, that, I mean, are there scenarios in which you round the corner and you replace sort of two segments with exactly one segment? Or that can't happen?
Yeah, so for example, like, you mean like this, and then
Well, no, I mean, in this case here, you have sort of two copies of the same one. Oh, for the green one. Ah, you're right. Okay, good. Okay, good.
so right. So there's only one. Like this is a straight single segment, right? Okay, good. So now I want to generalize this to a more general contact form. So what do those look like?
Just a quick question.
Yeah.
The reason that we know all the curves is because it goes out.
Yes. Yeah. To show the existence, you have to use. So it's based on induction, and the base case is the work of Taubes on three-puncture spheres. Yeah, in his paper, Holomorphic Beasts. Yeah. Mm-hmm. Yeah.
I would sort of would have expected that the curves all could have been found sort of more directed, but maybe that's just doing what Taubes does in that case. I mean, T3 is sort of a nice enough setup that I would hope that perhaps you could just tinker and find all the curves.
Maybe, but not that I know. So when you have a one form on let's say some arbitrary interval I cross T2, so this is x and this is T1, T2 coordinates. The condition that this is a contact form is that f comma g cross, this is the usual cross product. Cross f prime g prime is greater than 0. So pictorially, when you draw the graph of f comma g, it means that this radial vector is rotating counterclockwise. So anytime that happens, this lambda is going to be a contact form, and I would like to know what is the ECH, what is the combinatorial description of the ECH for that lambda, or more precisely, some small perturbation of that lambda. So the next simplest case would be, well, maybe it just looks like this, right? So in this case, again, there's S1 family of orbits whenever, again, f prime over g prime is rational. And again, after perturbation, you're going to get two wave orbits corresponding to the two critical points of the auxiliary Morse function. But they're slightly different. So I'll write E hat for the elliptic orbit. And this time, this elliptic orbit corresponds to the min of the auxiliary Morse function. And there's a positive hyperbolic one, which I denote by H hat. And it's straightforward to check that in this case, you're going to get exactly dual differential. So by that, I mean, so in this case, you get a dual differential. So instead of rounding the corner of alpha to get beta, you're going to round the corner of beta to get alpha, right? So let me just illustrate this by an example. So if you had, so in this case, the ray vector field is rotating clockwise. So the corresponding polygonal paths are all going to rotate clockwise as well. So suppose you had h hat and h hat. This could have been obtained by another orbit set. Let's say E hat and H hat, right? So this is obtained from this by rounding this corner. But in this case, the differential of the red path, so which is H hat minus 1, 1, E hat 0, 1 is H hat minus 2, 1, H hat 1, 1. Right? So it's the dual picture to the original one. So in the hybrid case, let's say f comma g looks something like this. So there are some regions where ray orbit is rotating counterclockwise, and there are some regions where it's rotating the other way. So again, after perturbation, you're going to get two ray orbits, what are called convex ray orbits, when f prime over g prime is rational, and ray orbit is ray vector field is rotating counterclockwise. And so I'm going using the notation from earlier, I'm going to denote these two ray orbits by E check and H check. And then there are two concave. So these are the definitions for convexity of a ray orbit in this setting. When the ray vector field is rotating clockwise. And I denote these two by E hat and H hat. And I also mentioned that the Conley-Zander index for these orbits, so these are, well, embedded. With respect to the natural trivialization given by the identification I cross T2, for each of these four types of orbits is that this is 1 and this is 0. So 1, 0, 0, and minus 1. So that's why earlier when I said the elliptic convex orbit corresponds to the max of the auxiliary Morse function, and this one corresponds to the min of the auxiliary Morse function. That's why this one differs by 1, this one being 1 greater than that one, and the other way for the other pair. So So in this general case, this rounding and the dual of rounding could be occurring at the same time. So we need a new we need to extend the definition of rounding corners. So here's a list of definitions that will be used to describe the differential. So these are all pretty straightforward. So as before, we can form polygonal paths from polygonal path P alpha from an orbit set alpha written in ordered product notation. And in this case, we also need to keep track of the x coordinates that this orbit occurs, because, for example, you wouldn't be able to distinguish this one and that one. So you need to keep track of which ones they are. And for a pair of paths P alpha and P beta, where alpha and beta are in the same homology class. So that means the corresponding paths have the common starting and end points. We're going to consider the area between these paths is called polygonal region. Region R, and we write these two paths as the positive boundary of the region and negative boundary of the region. Right? Okay, next. So an edge, so I forgot to write this down, but an edge refers to a primitive vector that's occurring in a path. So an edge B of the region R, which means the whatever edge that's occurring either in P alpha or P beta, is called extreme. If its x coordinate, so remember each edge now carries the information about which x coordinate it occurred in. So xb is either mean of all the x coordinates of the edges in the boundary of the region, or max. Right? And a region R, so sorry about this long list of definitions, is called local if all edges have the same x coordinate. So just a few more. R is called decomposable if it can be written as concatenation. So I'm not going to define a concatenation, but just illustrate by a picture. So for example, a region between this and this, for example, would be considered decomposable because it can be written as concatenation of these two indecomposable regions. Or even this one. Can be also decomposed into concatenation of two regions. So if you can't write it as a concatenation of two regions, then you call it indecomposable. So it's concatenation between this bigon and then this triangle. Okay.
All the edges have the same x coordinate. What's that?
Right. So I sort of suppressed it.
Is there any picture like that?
When all the x's have the same x coordinates. So for example, there could be a bigon corresponding to, say, elliptic and the hyperbolic that's occurring at the same point x over here. So in fact, that will come up later when I give some examples of differentials. So maybe I should skip this next definition and should I? Well, let's try to cram everything. Right. Let's try to cram everything in there. So a slice class of a region R at x naught is minus of the sum of all the edges occurring in the positive boundary of R with x coordinate less than x naught plus sum of all the edges occurring in negative boundary of R with x coordinate less than x naught. And to put this into more perspective, if C is a holomorphic curve in the moduli space of curves from alpha to beta, and R is a region between P alpha and P beta, then the slice class at x naught is the homology class of C intersect the slice at x naught, right? Okay. I promise just a couple more. And a region is called positive with respect to lambda if at every x in the interval, the rev vector field expressed in R2, which is a tangent space of T2, cross this slice class is non-negative. And a positive region R is called minimal if it contains no internal lattice points. So roughly what the positivity says is that the path of alpha should stay on the right side of the path for beta. So for example, something like this cannot occur, right? So before, most of the pictures look like something like this, where red path stays to the right, so the right side of beta. So this is positive, this is not, and for example, this also would not be positive, right? So roughly that's what the positivity is saying. And once it's positive, then you can count the internal lattice points, and it's minimal if it contains nothing. So earlier when you were asking about the straight line, whether the straight line is in the counting towards the differential, it didn't because it contained the internal lattice point. So that's exactly what I'm going to state. So that's the theorem, which is a generalization of this.
There's something about positivity like this in the Hutchings-Sullivan paper as well, but you didn't mention it.
Yeah.
Was that just the condition that the alpha path is, I guess, right below the beta path?
Oh, right. Yes. So yeah, okay. So in this case, yeah, I guess you're right. In this case, I should have stated that the alpha path stays to the right of beta path here as well. Yeah, thanks for pointing that out. So the theorem is that, again, assuming some nice perturbation of the lambda, the general lambda that I guess I erased, that looks like then let alpha and beta be admissible orbit sets of lambda in I cross T2. And then the differential coefficient is non-zero if and only if, again, if alpha can be written as some common orbit sets with something differing in the middle, and the region between alpha path and beta path is, so all of the definitions, did I erase some of the definitions? Okay, so all of these definitions from 4 through 8 comes into play here, is positive with respect to lambda. It has to be non-local, has to be indecomposable, so it's not decomposable, and minimal. So that describes the geometry of the polygonal region. And I also have to describe how to label and all edges are labeled. So that an alpha edge is labeled H check if it's extreme, or E hat otherwise, and a beta prime edge is labeled H hat if extreme, and E checked otherwise. So except exactly one edge where you replace E to H or H to E without changing the convexity of the label. Okay, so that's the statement. So probably don't have time to say anything about the proof, but let's go back and discuss some of the examples that we've already seen. So in the first example, for f comma g that looks like the circle in the original T3 paper, you had rounding corners giving you the differential. And what this is saying is that, okay, alpha edge is you're gonna initially label them. So in this case, the ray orbits are vector field is rotating counterclockwise. So this one happens first, and then these two happens somewhere around here, and then that one happens. So this happens first, and then these two happens, and then that happens, right? So vector field is rotating this way. So this one and this one are extreme edges. But this one happens first, and this one happens the last. And these are non-extreme because they happen in the middle. So I'm going to label it H check, and then these guys are E check because they're not extreme. And then I pick one, for example, pick this one and then replace H to E. Or I could have changed any one of them, and they all contribute to the differential. So this agrees with the original description of the rounding corners. And similarly for the dual picture, and I'd like to give a few more examples.
Maybe try to finish up.
Right. So in the more general case, where the graph of f comma g looks something like this, I could have a bigon with two alpha edges. So for example, I could have these two. So it's a degenerate polygonal region where initially I would label them H check and H check according to rule up to this point, and then I get to replace one of them, for example, this H into E. Then this one will correspond to a holomorphic curve. For example, a holomorphic cylinder with two ends, one of them at E check, and the other one at H check, occurring here and here, right? So there are these kind of curves that corresponds to the differential. So E1, 0, H minus 1, 0 check is the empty set, empty orbit set, right? Because there's empty beta path, right? So it corresponds to the empty orbit set. So just a couple more examples. So there could be a bigon with one alpha edge and one beta edge. See, this happens if, for example, these two convex and concave orbits are involved. So let's. So again, now this orbit occurs first, and then this orbit occurs. So they're both extreme. So initially, you would label the first one, the alpha edge with H check, and then the second beta edge with H hat. But you get to replace one of them, for example, with E like that. And that also contributes to the differential. So in this case, differential of H check 0, 1 is E hat 0, 1, right? And the more general case would be so this is the last one. So in this case, you have something that looks like so you have H check, H hat, H check, and then E check. So this E check happens here. H hat happens here, and then H check happens here. So in this case, what happens is that this convex orbit happens first, and then the next one, this orbit happens, right? At this point, the slice class will be something like the end of the partial path, alpha path to the partial beta path. And then H hat happens here as an alpha edge. And then finally, H check happens at the end. And I already labeled it so that it looks like it follows this rule. So initially, you would have had these two extreme edges labeled hyperbolic, and then these two non-extreme ones as elliptic. But I get to pick one of them and just replace it. So this will also correspond to a differential. For example, in this 1, 0, H hat 0, 1, H check minus 1, 0 would contribute to E check 0, 1. So you can, so it's pretty simple combinatorial description, and you can build all sorts of pretty much any kind of holometric curves that you desire using this way, and they all contribute to the differential. So unfortunately, I don't have time to say anything about the differential, but I'll be happy to talk to you about any of these and possible applications of this idea for symplectic capacity problems and so on. So that's it.